Hi everyone. Today we're going to be learning a bit about the effects of traveling at very, very high speeds. So we've already talked a little bit about the relativity of simultaneity. Today we'll be talking quantitatively, rather than just qualitatively, about how time and space change when we move at relativistic speeds. That is, speeds close to that of the speed of light. To begin with, we're going to be talking about time dilation. Now, you've learned in your previous years at high school about classical physics and Newtonian physics. And in these sort of physics, we always assume that time is this constant, unchanging quantity that's the same for everyone. So if you measure a second while you're standing still, then it will be the same length as a second measured by someone moving very, very fast. So time is the same for everyone. But as we'll find out, in Einstein's special theory of relativity, this does not hold true, and time can change depending on how fast you're moving. So, one of the big differences between classical physics and relativistic physics, that is, the physics discovered by Newton and the physics discovered by Einstein, are that time is not absolute. It's not a constant, unchanging quantity. So it is possible to make a quantitative measurement of exactly how much time changes. And the amount that it changes by will depend on the velocity of the traveller. At very, very low velocities, such as might be seen every day on Earth, we'll find that there's not much of a difference, which is why, of course, Newton was unable to put it into his own laws. And in fact, we can calculate this difference for any inertial frame of reference. Remember that in Year 12 we're looking at special relativity. Special relativity only covers the special case of inertial frames of reference, which do not speed up or slow down. They only move at constant velocity. If we wanted to look at accelerating frames of reference, we would need to learn about general relativity, which works for the general case. That is, any case at all. Now, Einstein figured out exactly how time changed by using a thought experiment. Just like for simultaneity, he couldn't exactly get a spaceship traveling at the speed of light. Space travel was still a few decades off. And so he used the power of imagination to figure out this hypothetical scenario that would teach him how time changed when objects were traveling at high speeds. So once again, we have a very fast-moving train. We have some beams of light traveling through it. And all we're going to do is fire a beam of light from the floor of the carriage to a mirror on the ceiling. And we're going to time how long it takes. What we've set up is basically a clock, right? A clock measures regular intervals of 1 second or 1 minute or 1 hour. Our clock here will be measuring an interval much, much shorter than that. Just the interval it takes for light to go from the bottom of the train up to the top of the train. So as you can imagine, the seconds that it's counting are going to be much, much shorter. So here we have an animation of what such a light clock might look like from the passenger's point of view inside the train. So all we have is a beam of light coming from a light at the top of the carriage, going down to the bottom and reflecting from a mirror. So the light goes all the way down and all the way up. Notice that we just have a straight line going perpendicular to the ceiling and the floor, right? If we were to draw any sort of diagonal line like this, it would be much longer. That'll become important in a moment. So, because we can measure the height of the carriage, we can figure out the total time that the beam of light will take is simply given by this equation here. The time that it takes to go from the floor to the ceiling, or from the ceiling to the floor, is simply given by this. Time equals distance over speed, right? That is, t0, the time that we're measuring in the rest frame where the light's not moving, equals h, the height of the carriage, over c, the speed of light. Fairly straightforward, right? Now let's look at this in a different frame of reference. We'll look at it in a frame of reference where instead of being stationary, the train is moving. Now when we're outside the train and the train is moving, we can see that in order to go down to the bottom of the carriage and bounce up, the light is actually traveling in a diagonal path. Instead of just going vertically, we have to start at a point over here, travel downward, and then bounce up until we reach the ceiling again. And so you can see that we're traveling a much longer distance than we were before. So will this trip take the same amount of time? Well, no, it can't, because the light has to travel at exactly the same speed to all observers, right? That's what one of Einstein's postulates was when he was defining his special theory of relativity. And in fact, it follows from the principle of relativity. If we measure that the light was traveling at a different speed than what we expected, then it means that we'd be able to tell that we were moving, or that the train was moving with respect to us. So we have to measure the light traveling at exactly the same speed, except it's moving over a longer distance now. That means it's going to take a longer time. So we can use some complicated mathematics in order to figure out exactly how much time that will take. What we do to figure this out is we compare the vertical time, that is the time in the rest frame where the light just goes straight up and down, to the time it takes when the train is moving. You can see that we're going to get a right-angled triangle here. We know that this edge is simply going to be the height of the carriage, whereas this is going to be the square root of the height of the carriage squared plus the length of the triangle squared, right? And we can figure this out by looking at how fast the train is moving. And so that's explored in the working out over here. We can see that the time it takes for the light to travel diagonally equals the movement of the train squared plus the height of the carriage squared. Substituting in the height of the carriage squared with our expression that we got when we're looking at the rest frame, we end up with this equation. And then, algebraically manipulating it, we'll end up with this equation at the bottom. If you like, you can see if you can follow those steps along. So we end up with this equation here. TV, that is, the time that something takes when it's moving, equals T0, the time that it takes when it's not moving, over this expression here, which, as you can see, is related to V squared, or technically V over C, all squared. V is the speed of the rest frame, the speed of the moving frame, rather. So, if we're looking at a frame that is moving with respect to us at a speed v, this is how time will change within that frame. So here's our equation. We can see that this expression at the bottom is always going to be less than 1, right? We know that if we're moving at less than the speed of light, then v over c is going to be less than 1, but greater than 0, right? Because we're looking at the magnitude of the velocity, and we can't be any more stopped than 0. So that means that if we square the top and the bottom, we'll still be between 0 and 1. Now, if we take a number, 1, and we subtract this from it, then we'll end up with a number like this. We're still constrained by 0 and 1. If we take the square root of it, then we'll still be between those two numbers. Now if we take our numerator, t0, and divide it by a number that's less than 1, then we're going to end up with a number greater than t0. So that means that if we look at the time between seconds in a moving clock, that is tv, then the seconds will be longer than in a stationary clock, t0. So this means that clocks inside a moving frame of reference will tick more slowly than in a stationary frame of reference. That is, if we were to know exactly how fast clocks were moving inside a train moving at close to the speed of light, we would notice that those clocks were ticking more slowly than if we have a stationary clock. And this remains true no matter what you define as stationary. So if you say that we're inside the train and we're stationary, then a clock outside the train will appear to be moving. And that means that the clock outside the train will be running slowly. It's getting kind of weird now, isn't it? But there are measurements that we can make that show that this really happens in real life. The effect is called time dilation because we have time and it's getting bigger, it's dilating. If we were to graph exactly what TV over T0 looked like, it would be something like this. If you want to try graphing it yourself, the equation will simplify to something like y equals 1 over the square root of 1 minus x squared, where instead of x we have v over c. That is the velocity of the frame of reference relative to the speed of light. Or if you're a fan of indices, you might just replace the whole thing with 1 minus x squared to the power of minus a half. So graphing this, we'll end up with something that looks a bit like this. And you can see that it's asymptotically approaching 1. Now, we can also see that if x is any greater than 1, then we're trying to take the square root of a negative number, and we'll end up in the imaginary realm. On the other hand, if x is exactly 1, then we'll end up dividing by 0. So we can see that x is going to have to be less than 1 at all times. And of course, we can't get any more stationary than a speed of 0. So the time that it takes for an event to occur in its own rest frame, that is t0, the frame in which it's not moving, is called the proper time of the event. So this is the second that a clock counts out if the clock is not moving, right? And if we see what TV looks like, that is, the length of a second when the clock is moving, we can see that it's always going to be greater than when the clock is stationary. Over here, where v equals 0, that's going to be the proper time of the clock. No matter where we are on the graph, we're always going to be greater than this proper time, as long as we're not exactly at 0. Another feature of this graph that we can see is that until we're getting really, really close to the speed of light, there's almost no noticeable change. Even if we were moving at a tenth of the speed of light, which is extremely fast, something like 30 million meters per second, then we would notice barely any time dilation, because we're almost exactly still at 1. It wouldn't be until we reached more than 80% of the speed of light that we'd start to notice the time dilation going up by factors of 2 or 3. Now, when of course Einstein first came up with this, he wasn't really able to test it. There were simply no objects that could be measured that moved this fast that we could look at the timing of, right? We didn't have clocks that we could accelerate to 90% of the speed of light and see them run half as fast. But today, we have observed time dilation in real life, so it's no longer just theoretical. It's an experimental proven fact. And we've seen this in two different types of fast-moving objects, the very small and the very big. And respectively those are in tiny muon particles. Muons are subatomic particles that you might learn more about if you study quantitative quarks. And orbiting satellites, which are of course quite large. And these are things like GPS satellites that orbit the Earth. Now, we know that in space there's a lot of radiation everywhere from all the stars, right? This means that occasionally we'll get very fast-moving, very high-energy particles striking the Earth. Luckily, they're blocked by our upper atmosphere. But the thing is, sometimes these cosmic rays can produce tiny, highly energetic particles called muons when they reach our atmosphere. Muons are a little bit like electrons, but heavier and very, very unstable. They're moving because of their high energies and the energy of the cosmic ray that created them at almost the speed of light. Not quite the speed of light, but very, very close. Within 1% of the speed of light, in fact, which is mind-bogglingly quick. And because the upper atmosphere is so high up, and they're moving at almost the speed of light, it takes them about 16 microseconds in order to reach detectors on the ground. That is about 100th of a millisecond being 1,000th of a second. So it's really very, very fast. But I mentioned before that muons are not very stable. In fact, they're very unstable indeed. If we want to measure how long they last, then we can create them in a laboratory and test them. So when we create a muon in a laboratory, we'll notice that it only lasts for about 2.2 microseconds. So after this, they'll turn into other subatomic particles like electrons and neutrinos, and effectively they'll disappear and we won't be able to detect them anymore. Now hang on a moment. These muons that we're creating roughly stationary last for about 2 microseconds. But the muons created by cosmic rays last 16. There's a difference going on here. Surely if we had muons created in the upper atmosphere, they wouldn't last as long as they needed to get all the way to the ground. There's simply not enough time. But remember, time is not the same for everyone. The time in a cosmic muon's frame of reference, because it's moving at so close to the speed of light, is dilated. That is, when we measure 2 microseconds, the muon measures much less than that. And when we measure the 16 microseconds that the muon takes to get all the way down to the bottom, the muon will be measuring less than 2. And so the muon will survive. This explains why they can get all the way down to the ground and last what looks like, to us, 16 whole microseconds, which according to themselves, they are only lasting 2.2. Now at first you might think that it's just some sort of illusion, it's due to, delays of light traveling or something like that. This is not the case. It is in fact time itself warping with the moving object. So time is not the constant quantity we thought it was. These muons actually last longer than if they were stationary, because they are moving, and if they had onboard clocks, so to speak, those clocks will be running slower. It's not just light clocks that run slower, it's all clocks, because if you could figure out a discrepancy between the light clock and any other clock, you'd be violating the principle of relativity. You'd be able to tell that you were moving. So the other example of time dilation that we can see is in satellites. So clocks in orbit around the Earth tick slightly more slowly than clocks that are stationary on the surface. In particular, GPS satellites, which have to be very, very accurate because they measure the time that it takes for a beam of light to travel, have to compensate for this effect Otherwise, they'll slowly drift out of synchronization with the clocks on Earth that they're syncing up with. So an astronaut in orbit for 6 months will in fact age less than if he was on the surface. The thing is, because space shuttles don't travel very quickly relative to the speed of light, the change is only about 0.007 seconds, that is 7 microseconds, if they stay in orbit for a whole 6 months. That's because when we look at the graph of time dilation, we can see that if we're very close to zero velocity, then there's almost no noticeable time dilation. So that's the end of the theory. In this section, we've covered time dilation, what it is and how we can observe it. We've also looked at how time dilation varies as we travel at different speeds. So let's go on to some questions to test your knowledge. Question 1. Which of the following best describes time dilation? Is it A, clocks are never moving relative to an observer? B, clocks are always moving relative to an observer? C, moving clocks run slow? Or D, moving clocks run fast? Now, assuming we're talking about the time that the clock is measuring, and not in fact the motion of the clock itself, our answer is going to be C, moving clocks run slowly. Due to time dilation, if we look at a clock that's moving, then time will be passing more slowly for that clock than for clocks that are standing still with respect to the observer, right? So that means that if a clock is moving, the seconds that it measures last for longer than if it's not moving. Question 2. Which of the following statements is true? The proper time of an event is always larger than its time in a moving frame of reference. The proper time of an event is always smaller than its time in a moving frame of reference. The proper time of an event is always equal to its time in a moving frame of reference. Or the proper time of an event depends on the reference frame from which it is measured. Now let's start off by looking at the bottom two options here. Remember that the proper time of an event can only be measured from one frame. That is, the frame where the event doesn't move in space. So in this case, we can't say that it's D, because the proper time is always measured from exactly the same frame of reference. How about C? The proper time of an event is always equal to its time in a moving frame of reference. Now, if we were looking at classical physics or Newtonian physics, then C would be right. The time of an event is always the same, no matter how fast you're moving. But in relativistic physics, that's not the case. As we saw from the previous question, moving clocks run slow. So the proper time of the clock is looking at the time that it's measuring when it is not moving. When it is moving, time passes more slowly on board the clock. So in this case, the proper time of the event will be smaller than the time of the event when the clock is moving, right? And remember that this doesn't just apply to clocks, it applies to everything that is moving. And if people could notice that the clock was ticking slower, then they could know that they were in a moving frame of reference. It means that everything on board a very, very fast-moving train, for example, will be moving much slower than you would expect it to. And indeed, aging much slower than you would expect it to. Question 3. Two astronauts, moving at a speed of 40% of the speed of light relative to each other, are playing a game of chess via radio. Now, it's important here that I haven't said which one of these astronauts is moving and which one is stationary. We can define it how we like. What we're looking at is the difference between the proper time of an event and the relativistic time of an event. The proper time is always measured, of course, from the frame in which it isn't moving. So when we're measuring the proper time, we assume that the astronaut isn't moving. And when measuring the moving time, we know that our speed is this. Now, as they play chess, they take 1 minute each to make a move. And that, of course, is in the astronaut's own frame of reference. That is, the proper time. So how long does it take according to the other astronaut? So what we've got is an event that takes time, that is, moving in a game of chess, and that time is 1 minute. Right? So now we want to figure out how long 1 minute takes if the spaceship in which it takes place is moving at a speed of 40% of the speed of light. And that's where our equation comes in. Remember this? Our time dilation equation. Now we have a few variables here. TV is what we're looking for. The time that an event takes when the frame of reference it's in is moving. That is, the time that it takes to make a move in chess when we're in the other astronaut's frame of reference. So that's what we're looking for, TV. T0 is the proper time of the event. That is, the time that each astronaut takes to make a move according to their own frame of reference. So that's going to be the 1 minute. Right? Finally, we have c, the speed of light, pretty obvious, and v. And v, of course, is the speed of the spaceship that's moving. If we look at this carefully, though, we can see that we have a v over c all squared. If we take v over c from here, we just end up with 0.4. So we can use this as our value for v over c. Notice that this 0.4 doesn't actually have any dimensions. V is in meters per second and c is in meters per second. Dividing out the units means that we end up with a dimensionless quantity. So the entire denominator has no dimension. It's simply a number that we multiply t0 by. This means that if we start off with t0 in minutes, we'll end up with tv in minutes. So we don't need to bother converting to seconds. Now, let's make some substitutions. We can put in our 0.4 for v over c, don't forget to square it, the 1 minute for the proper time of the event, and of course, now all we need to do is evaluate this with a calculator to figure out our answer. We'll get, of course, an answer in minutes, because we're taking a dimensionless number and we're dividing minutes by this. We'll end up with 1.09 minutes. Or, of course, because we don't use 0.09 in our system of measuring time, we can convert that to minutes and seconds. It ends up being about 1 minute and 5 seconds. That means that even though we're moving at this incredible speed of 40% of the speed of light, which is a very fast speed indeed, we only get enough time dilation to change 1 minute into 1 minute and 5 seconds. Of course, over several hours or days, this difference would start to build up. Question 4. A muon is a subatomic particle that decays after 2.2 microseconds, on average, in its rest frame. How long does it take to decay if it's traveling at 99% of the speed of light? Now remember, real muons move at about 99.6% of the speed of light, so we're probably going to get a number that's a little bit smaller than the number I quoted earlier. So, once again, we're going to use our equation for time dilation. TV equals T0 over our factor over here. Sometimes people write this whole factor, 1 over the square root of 1 minus v squared over c squared, as gamma. And that makes this equation much simpler. It'll simply be TV equals gamma T0. Of course, while we're still learning it, it's probably more helpful to write it out in full. So, what are our quantities for the proper time, T0, and v, the velocity? Of course, if we've got 99% of the speed of light, then that will be 0.99 c. So we can replace this v over c with 0.99. T0, the proper time, is the 2.2 microseconds that we've been given. Substituting those in and turning microseconds into seconds, because SI units are good, we end up with this equation over here. You can see that the numbers have been substituted. It's a fairly simple step. We can use a calculator to evaluate this. We'll end up with 1.56 times 10 to the minus 5 seconds. Of course, it might be a good idea to compare this to a number in microseconds. And so if we say that there are 10 to the minus 6 seconds per microsecond, then by converting this to microseconds, we'll end up with 15.6 microseconds, which is almost 8 times longer than our original lifetime. So if we're moving at 99% of the speed of light, this is how much time sort of starts dilating and swelling up. Question 5. Is it possible for the occupants inside a fast-moving spaceship to measure time dilation within the spaceship? That is, measuring how fast a clock is ticking to figure out how much time is dilated? If so, explain how. If not, explain why not. So, are there any measurements that we could take inside this inertial frame of reference that would tell us that time is behaving differently to when we were stationary? Well, that's the principle of relativity, isn't it? So the answer has to be no. It is not possible to measure time dilation on any event inside the spaceship. If time dilation could be measured, then it would give you a way of measuring exactly how fast the ship was traveling, right? You say, oh, we're taking 7 times longer than normal to do things, so we must be traveling at 99% of the speed of light. You can't do that. There's no way to notice inside an inertial frame of reference that you're moving at all. So suppose you looked outside the spaceship. Suppose, in that case, everything outside the spaceship would appear to be moving. And so objects on the outside would be time dilated, because they're moving objects, and moving clocks run slow. So in the spaceship's reference frame, it is stationary, and everything outside the ship is time dilated. So if there were 2 spaceships passing each other in an empty void, then each one might say that they were the stationary one, and the passing spaceship is slowed down and has time dilated. Remember though, that neither of these is an absolute correct frame of reference, but they both make a correct observation in their own frame of reference. That's the end of the questions. We've gone through some pretty mind-boggling stuff here. That is, that time is not the same for all observers. It slows down inside a moving frame of reference. We've looked quantitatively and qualitatively at exactly how that time dilation works, and exactly how it changes as we get close to the speed of light.